And our speaker today is Andrea Bianchi from University of Copenhagen, who will tell us about an upper bound on the topological complexity of discriminantal varieties.
Thank you for the invitation to give a talk. So before introducing these discriminantal varieties, let me tell you what the motivating problem is for the entire talk. So let me remind you what configuration spaces are. So in the entire talk, n will denote an integer, at least 2, and I will consider the space Fn, which is known as the ordered configuration space of n points in the plane. So we take n tuples of points in Cn, and these points are required to be distinct. And there is an ordered counterpart, which is known as Cn, and is obtained by the previous one by quotienting by the action of the symmetric group Sn, which permutes the labels. And the question that we try to address today is how much is the topological complexity of Fn, and how big is the topological complexity of Cn. Okay, if you look for applications in engineering for topological complexity, then one can say that these are the right kind of spaces one should look at, because suppose you have a system of robots who have to move in the plane and have to coordinate avoiding collisions, then a motion planner for this system of robots is precisely what can be studied in terms of the topological complexities of these spaces. And there are two cases where the robots are ordered. So there is robot number 1, robot number 2, and so on. And here instead, the robots are indistinguishable. So this problem is not new to literature. There are some results already. Let me mention them. The first goes back to Faber and Justinsky, who prove that the topological complexity of the order configuration space is equal to n minus 3. So they give a complete answer in the order case, and then there is a result by Grant and Ratiometer, who consider some space which is halfway between Cn and Fn. This is this configuration space of points of collections of points of two colors. So so they will compute TC of this space, and it turns out it is equal to twice the total number of points minus 3 as well. Let me make a picture to explain you what space this is. So a configuration in this space will consist of distinct points in the plane, but some of them are blue and some of them are red. And we require that there is a total of blue points and a total of red red points. And there are some in this result we need some mild conditions on these two numbers, which let me skip on that. Let me just say that this result doesn't cover the case of Cn, because both of these numbers must surely be positive. But still, it's a result that goes, I mean, you see the result is twice the total number of points, minus 3. Here in the order case is twice n minus 3. So one can already get at least a conjecture what the answer here will be. And before spoiling the conjecture, let me say that there is also some previous work of mine with ratio meter. We consider the topological complexity of unordered configuration spaces, but more generally in a surface. So sigma is a surface, for example, this one. And we take configurations of undistinguishable points on that surface. And again, we obtain some results in many, so we sector many sigmas, but not sigma equal to the plane. And the reason is that in our method, we use that the surface has non-trivial first homology. This is an important ingredient in our argument. Let me also say that there are very different techniques behind this all these results. So here we use the homology of the underlying space. Here, this space CBR is treated as a spherical space, and so let me say that this result uses work of Grant, Lupton, and Oprea on TC of spherical spaces. And here we also use this result in for surfaces, but the difficulty is applying finding an answer for the plane. Okay, so this is a rough sketch of what the literature already says, and let me now make an important remark, namely that the Lie group S1 acts by rotations on this space Fn and Cn.
We can't see what you're writing right now.
Sorry, I should scroll. Yes.
There you
so
go.
the group S1 acts by rotations on these spaces. Like you have a configuration, you can in the plane you can rotate it, and I mean one thing that one could wish is a motion planner on Cn or on Fn, which is compatible with the action of this group. What do I mean by this? Suppose that you have a couple of configurations. Let me work in the space C2. So suppose this is a configuration and this is another configuration. I can rotate both of them, let's say by 90 degrees, and I should obtain this picture, right? And now one thing that one could wish from a motion planner is that if the motion planner prescribes this path in the configuration space to move from the first to the second, then it should also prescribe the rotated path to join these two other configurations. I mean, from a point of view of engineering, this might be good because think that your robots are governed by a system that watches them, observes them, and measures where they are and where they should be. Then such an algorithm is good because the behavior of the robots would be independent from the point of view of the observer that observes them and coordinates them. I mean, this leads us to the notion of equivariant topological complexity, which, for completeness, I should remind. So this definition is due to Coleman and Grant. So sorry, We have a problem with the ink. So let X be a space. I mean, let's assume it's a CW complex with action of Lie group G. Okay, then we can consider, as in the classical topological complexity, we take the path space vibration, but now there is an action of G on the path space of X by this. This is the free path space. Okay, so this contains all maps from the interval to X without any base point condition of any kind. And this pi is the source and target map. So there is an action of G on Px by pointwise action, and similar there is a coordinate-wise action of G on X times X, and this map is clearly equivariant. It's G equivariant. So now we can mimic the classical definition of topological complexity and of motion planar. So first, G motion planar consists of the following two pieces of data. So first is a decomposition of X times X as a union of open sets, which must also be G invariant. So the action of G on X times X restricts to an action on each of them. And the second condition is the second piece of data is to give on each of these open sets a section of the path vibration. So it's equals to Px, and this must be a G equivariant section. And the definition of equivariant topological complexity is the minimum K such that there exists a G motion planar as above. I mean, a G motion planar in which X times X is divided in K plus 1 open, is covered by K plus 1 open subsets. Okay, so this is the definition, and to make sense of this definition, I mean, there is a remark that we need that X is G connected. This is a little technical. What does it mean? It means that for every subgroup H of G,
Pull your page again, please.
Sorry?
Move your page up. There you go.
So we need the G, sorry, that for every subgroup, the fixed point subspace, so we consider the subspace of X containing all points that are fixed by the entire subgroup H, and this must be empty or path connected. Okay, this condition that it can be empty is, I mean, Coleman and Grant give also the notion of G connected, and they ask that this subspace is just path connected and non-empty. But actually, for us, it would be okay if for some subgroup H there are no H fixed points. And the other remark that I want to make is that the topological complexity of a space is with a G action is bounded both from the topological, from the equivariant one. This should be clear. If you have a motion planner, which is also G equivariant in particular, you have a motion planner. Okay, so we wish to study, we introduced this definition because we want to, we would like to study the topological complexity of these two spaces in the equivariant setting. So to make the problem more interesting. And okay, so let me now tell you the first theorem. Let me call it theorem A. The first theorem says that the topological complexity is one equivariant of Cn is at most 2n minus 3, and also in the order case. And from this, we obtain immediately the desired corollary. So in the unordered case, we have 2n minus 3 lower or equal than the topological complexity of Cn, and this inequality is contained in previous work with ratiometer. Then we have the standard estimate with the equivariant topological complexity, and then by the result I just mentioned, we have also the upper bound, and similarly in the order case we have 2n minus 3 is equal to the topological complexity of Fn, and this is Farber and Ilczynski. This is at most the S1 equivariant topological complexity, and this is again by the above result at most 2n minus 3. That is, all the numbers I've written in this corollary are equal to 2n minus 3. So we get an answer to what is the topological complexity and also what is the equivariant topological complexity of the spaces Cn and Fn. And this is the motivating problem for which the rest of the talk that motivates the rest of the talk. Okay, so this theorem will follow from a more general theorem, which is the place where this discriminantal varieties will show up. So so the theorem is the following. Let me call it theorem B. So let V be contained in a complex space Cm and be the complement of the zero locus of a polynomial delta of the variables z1 up to zm. Okay, so I will call this a discriminantal variety. So this is my definition of discriminantal variety. So in particular, this inclusion is open. Okay, you can think of V as an open subspace of Cm, and now assume the following: that for some S at least 0, the torus Ts acts on V by scalar multiplication. I will tell you in a second what I mean by this. Just imagine this is a very simple way in which torus can act on this variety. Very algebraic. Well, I mean, it's an algebraic way, and it has very simple formulas. And suppose also that for every point in the variety, the stabilizer of this point, which is a subgroup of the torus, has a dimension at most t, for some t. Then, I mean, this condition really means what? The orbit Ts times p, which is containing V, as dimension at least S minus t. What is the condition? Sorry, the conclusion. The conclusion is that the equivariant topological complexity of this variety V is at most 2m minus S plus t. And this is the theorem that implies, I mean, the more general theorem, which an application of which is the previous theorem. Okay, now I owe you a definition. What is scalar multiplication? Definition. Okay, let me first say what it means that S1, a single, I mean, one-dimensional torus acts on V by scalar multiplication if there are integer C1 up to Cm such that, well, for theta in S1, I have that theta acts on the points Z1 up to Zm by multiplying separately each coordinate using the xi's as exponents. But as you see, it's a very well-behaved action of S1 on V, and let me just say that Ts acts on V by scalar multiplication if every factor does. I mean, this is Ts is the S-fold product of S1. Okay, so this is the definition of action by scalar multiplication. Okay, let's see how this theorem implies. I will now discuss how this theorem implies theorem A in the unordered case, and then tell you a little the strategy of the proof of this theorem B. Okay, and in the end, I will tell you what problems, I mean, what obstacles I see for future developments of the theory, but I mean, maybe there will be future developments as well. Okay, so so the application to Cn. Okay, so what is Cn? Well, Cn. How do we find? I mean, how do we cook up a discriminantal variety starting from a configuration space? Well, the answer is in the fundamental theorem of algebra. So the space Cn is homomorphic to the space of polynomials in one variable p of w of the form w to the n plus a(n minus 1 w to the n minus 1 plus a0, such that the discriminant of the polynomial, which is really itself a polynomial in the variables being the coefficients, doesn't vanish. Okay, I hope that this is known. And then we can consider a subspace of this Cn. So this Cn, I mean, this, if we see it in this way, this will live inside C to the n. Right? We have n coefficients for such a polynomial. But this is not yet the right space to, not yet the optimal space to consider. We have to consider this Cn0, which are those configuration with a barycenter at 0 in C. Right, this is a subspace here, and since every configuration here can be translated in a quite standard way, so that its barycenter lies at 0, and since this operation is also evidently S1 equivariant, we get that not only this inclusion is a homotopy equivalence, but it's also an S1 equivariant homotopy equivalence. Now, the equivariant topological complexity is an equivariant homotopy invariant. So we can equally well try to estimate, find an upper bound for the equivariant topological complexity, S1 equivariant topological complexity of this space. What is here the corresponding subspace? Well, we will have polynomials. I mean, the correspondence from here to here is given a polynomial, take its configuration of roots. Now, saying that the barycenter of the roots is at 0 is equivalent to requiring these coefficients to vanish. So here I will have those polynomials that look as follows. So we start from a(n minus 2, and then there is still the condition that the discriminant, which now is really a polynomial in n minus 1 variables, and it should not vanish. And this now is contained in C to the n minus 1, and it's again it's a discriminantal variety. It's by the very definition. Okay, this is the discriminantal variety. This is the V to which we want to apply the theorem, and now we know that S1 acts on V, and one can check that it is an action by scalar multiplication. And moreover, the very important thing is that the stabilizers are finite. So it's very easy to see here on configuration space. If you rotate configurations, the set of angles for which you get the same configuration is a discrete set of angles. Let me mention that if the fact that this stabilizer can be finite and yet non-trivial is the reason why the technique of Grant and Resch-Mitter works in the bicolor case, but not in this case. It's essentially the same. They formulate in a different way, but this is essentially what's going on. And they need stabilizers for their argument. They need stabilizers to be trivial and not just finite. So then we apply the theorem, and we get that the topological complexity as one equivariant of Cn is at most 2 times n minus 1 minus 1 plus 0. And this is exactly theorem A in the unordered case. Okay, and now let me tell you what the strategy of the proof of the main theorem of theorem B is. They should have a better pen. This makes too many spots. Anyway, the first idea is to, I mean, topological complexity is classically bounded above by the Lusternik-Schnirelmann category of x times x. And there is an equivariant analog of this. So use that topological complexity equivariant of space X is bounded above by the equivariant Lusternik-Schnirelmann category of x times x. So here again there is a definition in the work of Coleman and Grant. I use a slightly different definition, but which fits better to what I want to do next. But I mean, just to talk of this number, recall we have to check that that the space we want to consider, namely V, is TS connected, right? This was a condition, and then we will hope reduce to proving what, that the category T S equivariant of V times V is at most 2m minus S plus T. Now this condition that V is TS connected is the smallest part of the entire strategy of the proof, and it's also the one that requires all hypotheses. Namely, here we really need that V is discriminantal, and it's not just any complex variety or not even any affine variety. We really need of the form that I told you, and also need that action is by scalar multiplication, and not just any, say, any algebraic flavored action. And this is, I mean, this is the question that I would ask at this point is how can we get rid of this hypothesis? Can one recycle most of the rest of the strategy in other cases? Let me continue. Okay, now how are we going to prove that the equivariant Lusternik-Schnirelmann category of V times V is bounded by this? Well, in the classical case, you would prove that this space, we will try to find a homotopy equivalence of this V times V with a CW complex of dimension at most this number. And here we do exactly the same thing, but with an equivariant, a GCW complex. So show that V times V is TS equivalently homotopy equivalent to some TS CW complex with equivariant cells of index at most 2m minus s plus t. And now we notice, this space is a manifold. To approximate a manifold with CW complex, we are used to apply Morse theory. Now we are in the equivariant setting, so we need an equivariant version of Morse theory. And this is fortunately available. So, so the next sub point would be construct TS invariant Morse function on well, let me call it f from v times v into r with indices of critical points being at most 2m minus s plus t. And in this step, we really use the fact that V has a complex structure. Let me say here we need that V is an affine complex variety. And the construction of this Morse function is very similar if you know the Lefschetz hyperplane theorem. The argument is something of that kind. So here there is also very classical approach, and the last part, which is a little technical, one has to extrapolate from F TS CW structure complex, let's say, which is TS equivalent to V times V. And again, well, here the ingredient that we really need is just that TS is a compact Lie group. There is, I mean, there is this part of the proof is the most technical, but it's also the one in which we use less of the hypothesis. And it's a little a pity that only in this little detail we need most of the hypothesis. So let me conclude. I think I have 1 minute left. So let me conclude with a couple of questions. Maybe is it okay if I go 4 minutes?
Yes.
4 or 5 minutes. Okay, so let me conclude with, well, first question is, does this generalize to, let's say, to topological complexity of unordered configuration spaces, but in R3? As far as I know, these are not determined yet, these numbers. And I mean, one could try to estimate this TC with the SO3 equivariant topological complexity of the space. I mean, like in R3, there is an action of SO3, and one could try to play the same game. Well, here the answer is unfortunately no. But the reason lies in this connectedness hypothesis, no, because Cn of R3 is not SO3 connected. So how do we see this? Let me make a small picture. Here is a configuration of points, of endpoints. They all lie on the z-axis. So in particular, they are fixed by any rotation around the z-axis of any angle theta. Now there is another configuration in which I take on the xy plane, let me take a regular polygon. They must have the same number of points, so let's do this. And now this is fixed by rotation by theta equal to 2 pi over n. And now, in particular, both are fixed by 2 pi over n by this rotation, but there is no path joining these two configurations, which is fixed at all time by this rotation, but no path, which is 2 pi over n invariant between them. Okay, so this is the picture, and I mean, it would be nice to overcome this problem, and anyway to recycle the rest of the argument also in a higher dimension, but so far I couldn't do it. And let me also say a little about explicit motion planners. So do we get an explicit motion planner on Cn by reading carefully the proof and by doing concretely what is supposed to be done? Well, also here the answer is not quite. So at some point in the proof, there is a function. So let me simplify it a little. At some point, we need to classify critical points of S1 equivariant Morse function on Cn. Okay, this is a little part of what we have to do. You will remember maybe that in the proof the equivariant Morse function, where is it in the here? The invariant Morse function was defined on the product v times v. But how I really construct this Morse function is from a function that is only defined on each factor, and then I combine this function. So let me skip these details, and let's agree that we have to face a problem of the following form. There is G from Cn to R, which is S1 invariant. And now the problem is that classifying such the critical points of such a function is not easy. In particular, if we took G of W1, W n equal to the sum of the absolute values of wi to the square plus the sum of 1 over wi minus wj. Sorry about this. If we took this function, then the problem is known in the literature as the planar central configurations problem, and is solved as far as I know for n at most 7. There is a recent work by Moshura and Sklisinski. I hope there is someone in the audience who can help me with pronunciation, but the idea is that this is a difficult problem. Now, this function, this formula that I wrote, is not exactly what pops up in the proof of the theorem, but there is another formula which doesn't have better properties than this, at least as far as I can see. So if the problem is known to be difficult for this function, then it's probably also difficult for the function that appears in the proof. So also here one needs, for concrete motion planners, I think one needs new ideas. Okay, and this was the end of my talk. Thank you for your attention.
Thank you very much, Andrea. I open the Zoom for questions now, if anyone has a question.
I have a question. Let's see. You mentioned that if you replace the complex plane by R3, one runs into trouble. And in somehow this would be explained by the fact that the topological complexity for the order configuration space on R3 is one higher than you would have in the case of the complex plane. But if you go to R4 or any Euclidean space of even dimension, they have the same, the corresponding configuration space has the same value. It's independent of the dimension. It only depends on the number of particles. So the question is, what happens for R4 or any even dimensional Euclidean space?
So I don't understand what is the question. So in the order case, we know that there is only a little difference between odd and even dimensional, and you wonder whether it could be easier to, I don't know, start by looking at question. You would start from evaluating TC of Cn of R4. For example, is this what you suggest? Yes, I also thought about this, but at least the problem that I try to, I mean, this problem of not being, I mean, the entire strategy is to try to, let me say, attempt is to bound from above this topological complexity with something like equivariant topological complexity of Cn of R4 for G being a subgroup of the Lie group SO4. At least this is what I think the natural generalization of the attempt to higher dimension could be. maybe you want to consider the entire SO4, maybe you want to consider just some subgroup. Now, at least if you consider the entire SO4, and I guess at least if you consider G that contains an S1 inside SO4, so not even a maximal torus, just a torus, then you run exactly in the same problem that we have here. You can take an R3 inside your R4 and construct these two configurations, and they are fixed by some rotation. But I think you will not find because I mean to move these points lying in the plane, 2 points lying on this column, at some point you have to decide which of these points, of these endpoints, is the one that arrives at the highest position. And here you break a symmetry. So at least I mean I would be very happy if you or someone finds a way to adapt these ideas. There must be a way to use again the similar arguments in a higher dimension, but at least I don't see immediately how. In the order case, I mean, in the order case, it's also, let me see, in the order case, this problem doesn't quite arise, at least the configuration that I drew here, because if points lie in the plane, then any rotation, if these points in the plane are labeled, then no rotation which is not 360 degrees, I mean, no rotation will fix an order configuration. So this issue is also peculiar of the unordered case. So maybe the first, another thing that one could try to do first is the question, what is the SO and SOD equivariant of the ordered case? This might be an easier question. We know much more about order configuration space. Is this known? Actually, I don't know.
Okay, thank you.
Any further questions?
I have a question. Andrea, you know, there are different versions of equivariant topological complexity, the invariant topological complexity, Dronishnikov's example, et cetera, et cetera. Maybe some of those might be more appropriate to these problems. Then you don't need this G-connected business.
I see. I would be happy if another similar attempt can work. But I must admit I didn't think about applying other
Okay.
similar notion of equivariant topological complexity.
Yeah, they all sort of compete, and some of them are good for some things and others for other things, you know, so it's something to think about, I think.
Sure.
Okay, I'm going to stop recording, but if there are any more questions, we